Hi, my name is Thierry Tambe, and I'm presenting our paper, Algorithm Hardware Co-Design of Adaptive Floating Point Encodings for Resilient Deep Learning Inference. I am an EE PhD student at Harvard University, currently working on designing energy efficient and highly accurate hardware accelerators and systems for machine learning and natural language processing specifically. In order to obtain higher GNN compute density and energy efficiency, a plethora of reduced precision quantization techniques have been proposed. In this line of research, we observed that a majority of the proposed quantization techniques out there are mostly fixed point or integer based. Furthermore, these fixed point techniques are frequently evaluated on CNNs such as ResNet. However, emerging models such as natural language processing exhibit wide parameter distribution that cannot be faithfully represented by common fixed point or integer data types, and thus because of their inherent lack of dynamic range. So in this work, we address this shortcoming by proposing a floating point-based encoding blueprint for deep neural networks called adaptive float. Notably, the adaptive float algorithm is able to adapt to the statistical distribution of GNN parameters. Adaptive float is found to produce noticeably higher inference accuracies when compared to other deep learning data types, and it is resilient to aggressive bit-width compression. Finally, in this work, we propose a deep learning neural network processing element exploiting the adaptive float mechanism in order to yield higher per operation energy compared to integer-based hardware variants. So let's start by describing the adaptive float algorithm and how it adapts to the parameter distribution of the model. The adaptive float algorithm is floating point based, which means that it already offers higher dynamic range compared to an integer data type. Now, on a layer by layer basis, adaptive float further maximizes its dynamic range by formulating an exponent bias called EXP bias. EXP bias is notably computed from the maximum absolute value in the weight tensor. Then based on this EXP bias, adaptive float dynamically shift the exponent range of the data point in order to encode as faithfully as possible the larger values in the tensor. The adaptive float number system generally follows the standard floating point specification. However, we break from standard IEEE 754 compliance by not encoding floating point genormals. By doing so, we significantly simplify the hardware design. And it turns out that genormals are small enough not to encode, not to affect the inference accuracy of the neural network. Now, the main problem arising as a result of not using genormal is the lack of representation for the 0 point, because the 0 point is a floating point genormal number. In adaptive float, we solve this constraint by sacrificing the positive and negative minimum values to allocate the slot for the 0, as shown in this figure. We also note that the adaptive float algorithm is self-supervised in the sense that it only relies on the unlabeled data distribution in the network, and it can be easily plugged into any machine learning framework at learning or at inference time. And the user just needs to provide the input tensor, the required word size, and the exponent bit width. Now we will assess the resiliency of adaptive float during bit width compression. In our experimental setup, we consider 3 well-known neural networks across diverse applications, namely the transformer, an attention-based sequence-to-sequence network, and ResNet 50. We note here that these 3 networks exhibit relatively narrow to wide parameter distribution as shown on this table. Furthermore, for each of these networks, we evaluate and compare adaptive float against prominent data types commonly used in deep learning, namely uniform integer, posit, block floating point, IEEE-like float. Notably, in the POSIT and IEEE-like float, the dynamic range of these data types is fixed, which means that it does not adapt to the distribution of the data. If we were to look at the root mean square error computed across all the layers of the transformer model, we see that adaptive float produces the lowest average quantization error compared to uniform POSIT block floating point and float. Furthermore, we also note that among the self-adaptive data types, i.e. adaptive float, uniform, and block floating point, adaptive float exhibits the lowest error spread. And this observation is maintained when we look across models, data type, and bit precisions. We still see that in general, adaptive float produces the lowest average quantization error. Now, if you were to look at the accuracy trend for post-training quantization, we generally see that as the weight bit precision decreases from 16-bit to 4-bit, adaptive float, which is shown here in the red star, produces consistently the higher performance, whether we look at the transformer blue score, the sequence-to-sequence world data rate, or ResNet top 1 accuracy. And please refer to the paper to see the bare accuracy numbers. Now let us look at how we use adaptive float in hardware in order to obtain higher energy efficiencies. First, we note that a plurality of commercial deep learning accelerators implement monolithic integer arithmetic, such as NVDLA or the first generation GPU or the ML NPU. In these integer-based accelerator, we will see that in the computational data path, a high precision scaling factor is required to scale the partial sum. In contrast, we propose what we call a hybrid float integer PE, which provides a cost-effective compromise between the high accuracy of floating point computations and the greater hardware density of fixed point post-processing. The exponent bias values from the Western activation, which are extracted from the adaptive float algorithm, are stored in a single PE register. So there is very low storage overhead. Also, we note that during the conversion from floating point to fixed point, we use this exponent bias to shift the partial sum. We analyze the hardware performance by plotting the per operation energy in the top plot and the performance per area in the bottom plot here. Across Mach vector sizes, we can distill here that the hybrid float integer PE produces lower per operation energy compared to the integer-based PE. Although we do notice a higher area in the hybrid float integer PE. And that is because a floating point Mach is composed of multipliers, shifters, and adders, and it is not as compact as a fixed point Mach, which only contains multipliers. So in summary, in this talk, we made the observation that emerging deep neural networks, such as an NLP, exhibit wide parameter distribution that cannot be faithfully represented by common fixed point or integer data types. We address this shortcoming by proposing a floating point-based encoding blueprint for deep neural networks called adaptive float. Notably, adaptive float adapts to GNN parameters by shifting its exponent range on a layer-by-layer basis based on the maximum absolute value in a tensor. When compared against other prominent deep learning data types, adaptive float is found to be more resilient to bit width compression across models exhibiting narrow to wide parameter distribution. Finally, when adapted on a processing element hardware, adaptive float is found to yield higher energy efficiencies compared to fixed point solutions. So altogether, the adaptive float algorithm hardware co-design framework offers a tangible accuracy and energy advantage over fixed point solutions. Thank you, and I'll be happy to answer questions during the next session.